Good afternoon, everyone. My name is Greg Ristabin from Olympus. I'd like to welcome everyone to this webinar on new XRF technologies that will speed, simplify, and automate plant NDT PMI inspections. This webinar is a joint venture between Olympus NDT and Innovative Inspection Solutions. We have with us today as presenters Ken Smith and John Bailey. Ken is with Olympus and is one of the founders of Innovex Systems with over 20 years' experience in handheld XRF. John is with Innovative Inspection Solutions and is the inventor of the PMI patent for SGS. He has over 20 years' experience in the petrochemical industry. This webinar is budgeted for approximately 60 minutes. The main presentation should last approximately 45 to 50 minutes, leaving 10 to 15 minutes for questions. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the course of this presentation. The presentation, along with the Q&A, will be archived on our website at www.olympus-ims.com by early next week. Now, without further ado, I'd like to turn the presentation over to Ken Smith.
Thanks for joining us. We've got a lot of information for you today. I think that it will be useful. The first thing we're going to get involved in is just explaining a little bit about handheld X-ray fluorescence systems, handheld XRF. It's about the size of a cordless drill, weighs a couple pounds. It has a window where the drill bit would be that's about the size of a dime and allows you to send X-rays out into a sample. That's what we're going to be talking about. And pulling the trigger brings you a direct measurement of alloy chemistry and grade ID. We're going to talk about advances to this technology and the best ways to use it for PMI testing. And we're going to spend some time with my colleague John Bailey telling you about how you can sync our analyzer with field portable tablet PC to bring powerful PMI management tools out into the field. Tracking, recording, reporting, all that stuff is tremendously streamlined. Basically, this is the flow chart that we're going to be talking about. The handheld XRF takes the measurement, Bluetooths it to the tablet PC, where the components are identified, tracked, matched up to what they're supposed to be. The reports are generated. John will spend some time explaining all of that. And I'm going to jump in. The first thing we want to look at is to just give you kind of an idea of how this thing would work. I've got a certified sample of stainless steel 321 with its chemistry on your screen. And next to it, I have the display from the analyzer showing a 3-second test that we did, identified 321 as the grade. We show that 303 is a near match. We compare the measured chemistry, which is down here, with the grade spec. You can see that we measured titanium at 0.44, and that's actually the exact value in the certified sample. Manganese, 1.19. Here it is, 1.39. We've got copper at 0.39, copper at 0.41. So you can see how the system is tracking. What we're showing you basically what you see. These grades are typically identified in about a second or two. Just running 3-second tests in this case. Here we have a 4140 sample. Run the test, get a match. Shows the next closest match is 4130, and shows the grade specs down the right-hand side for the sample. And you can see our chrome measurement is lining up well with the cert. The manganese measurement is lining up well with the cert. And those are the grades. The moly, those are the elements that allow us to identify this grade as being unique from others. To take a look at a couple of grades that are very close to identical, I'm going to bring up both screens. Basically, it's the same test. You can see test number 32 and test number 32. What's different on this is over here in the right-hand side, we're comparing the sample to the 9 chrome plus vanadium spec. That's the best match. That's what it's automatically compared to. if I were to touch this part of the screen, it would toggle over to the second best match, which is 9 chrome. And it's showing us when we do the 9 chrome comparison why 9 chrome is not the best match. It's showing that vanadium is out of spec and niobium is out of spec, where they're exactly right on 9 chrome plus V. So that's the measurable difference that we zero in on in our grade library to be able to separate very quickly two grades that are 99.7% identical. The process of XRF has got 5 steps as we've described it here. This is showing the window that I described on the front of the system that's about the size of a dime. You would want that window to be on or near the sample. It doesn't have to be exactly on it, but the sample has to be in front of the window. It's best to put it on it. You pull the trigger to activate the X-ray tube, and then steps 2, 3, and 4 are really things that the user doesn't see. The X-rays excite the sample, knock an electron off, and as part of that instability, the system shifts its electrons around, emits a photon of energy that is characteristic to the element. We capture it as part of a spectrum of energy, and the part again that is visible to the user is that we come up with a grade match and a measured chemistry on the display. So pull the trigger, see the result. These steps are the things that go on in between. Here's another view of the same information. We've got the Bohr model of the atom, nucleus, electrons, orbital that the electrons are in. We shoot in our X-ray. An electron is knocked out of its orbital, knocked out of its shell. The result is that the electrons shift to go back to electrically neutral, and there's a fluorescent photon that comes out, and that energy will be specific to the atom that we've excited. So every element has a different signature energy that it emits. And this is just an animation of that process. Now, of course, we show ourselves ionizing 4 atoms and getting 4 different photons back, but in reality, XRF is a statistical method, and we can be exciting up to 100,000 photons in a second, not 4 in 4 seconds, and we process that information to determine the concentration in the sample. Here you're looking at the spectrum, and chrome has a lower energy than iron, than nickel, than moly, and the height of the peaks is directly related to the concentration of the element. So if there were twice as much chromium, we would have twice as high a chromium peak, and so forth. And then the part that is visible to the user is the display, where the chrome comes up not as a peak on an energy spectrum, but as the amount of chrome in the sample. So the way that it works is that we capture the spectra, we subtract out interferences, we make corrections for background and interfering elements. We apply our calibration factors to the net signal, and then what comes out of the other end is the elemental concentrations. The elements that we can test are circled here by the red boundary. Basically from magnesium to plutonium is what we can do. Magnesium is the lightest element that we can test. The things that we can't do that are common to real-world applications into alloy testing would be things like carbon, oxygen, nitrogen, sometimes beryllium or boron. Anything lighter than magnesium, lower Z number in this chart would not be measurable. We measure these elements, we normalize to 100%. That allows us to correct for size and shape, and that's the method that's used for field analysis. To give you an idea of the depth that our system penetrates, when people hear X-rays, they may think about high energy X-rays that go through things and are measured on the far side. That's not what we're doing. In this instance, I'm showing the thickness of a human hair If you had a piece of stainless steel that was 70 microns thick, like that human hair, what you would see would be basically that we would go in about 10 microns. Actually, we penetrate further than that, but not only do the X-rays have to go in to excite the sample, but the fluorescent emissions have to be energetic enough to get out. So most of what we see is in the first 10 microns of the sample. That means that it's important that you know that your surface is representative of what your sample is. If something is coated or plated, you're going to be measuring the coating, the paint, or the plating, and not the base material. So in that instance, you would grind. Paint, corrosion, metallic dust, sandblasting, shot blasting, things that people do to condition the surfaces of the metal. They can change the chemistry on the surface, and that's what we're measuring. So there are times when grinding is especially important to prepare the sample. If you're testing lighter elements because they're so weak, whereas a little bit of corrosion might not matter for looking at a stainless steel, if you're looking at aluminum grades, something where you're looking at light elements, the need for a clean sample is higher. Okay, this is samples that have been prepared and not prepared. It's an aluminum that we're looking at. On the first one where we didn't grind the sample, we didn't get a grade match. We saw a very high level of copper, much higher than we would expect in an aluminum grade. Told us there's something wrong here. We ground the sample, and once we did that, we got an exact match for AL6061. You can see the copper reading has dropped from 27% to about 0.3. So a clean surface makes a big difference. For grinding the surface, got a couple of ways that you can go at it. The Dremel, small battery-operated, easily portable item, especially good for softer materials where you're going to only occasionally need to grind. If you're doing harder materials or grinding every sample, the tool below is an angle grinder. It's a two-handed, powerful device that will clean up things pretty quickly. You have to pay attention to what kind of grinding material you're using. You don't want to be leaving traces of something that you'll measure on your sample. We find that zirconium grinding papers work quite well because they're generally hard and don't leave much residue behind or any. Something you have to pay attention to. Most of our tests are on the order of a few seconds, and that's what people like, is to be quick. But there are times when it makes more sense to run a longer test. In this case, I'm showing the 4140 that I showed you earlier. On the left is a 3-second test, and on the right, same sample, but I ran the test for 20 seconds. And what you can see that is different in the longer test is that we have nickel and copper at 260 ppm and 380 ppm that have shown up. So when you test longer, you get a better precision. You can see, for example, that the precision on the chrome was 0.03 in the 3-second test and 0.01 in the 20-second test, whereas not only do you get better precision if you test longer, but you get lower detection limits, and that's why the nickel and the copper are showing up. So if you want to make these kinds of trace level measurements, things that are below a tenth of a ppm or a tenth of a percent, you would run a longer than a few second test. Another reason to test longer is if you want to do light element testing. There's two things. Light elements don't have as strong a signal, and the second thing is that you have to run a second optimized beam in addition to the first beam to be able to measure these lighter elements. And we define light elements as magnesium, aluminum, silicon, phosphorus, and sulfur. And in this particular test, we shoot the stainless steel 416 sample that you see. It comes up right away and says beam 2 required. The instrument in a smart mode, if you run it that way, will tell you if you need to run a second beam to ID a particular grade. And in this case, we need to look for sulfur to separate 416 from 410. The system rolls over to the second beam, runs the test. I stopped it at around 20 seconds, and you can see there that we've picked up the silicon, we've picked up the sulfur, and actually we have a typo in our standard set. It's supposed to be a P for phosphorus instead of a T. And anyway, the phosphorus is also a light element, which was measured in this sample in 20 seconds. And those are nice readings. And 20 seconds isn't a terribly long time to get that kind of result. Another long test. This is the same kind of idea. We're doing a nickel grade, and here in the first test we only ran it about 6 seconds. We didn't measure the aluminum. We matched the grade to be WASP alloy. We looked at the grade spec and said, well, there's supposed to be aluminum in here. We know we didn't measure for it, but it's supposed to be here. So we're going to put in the average expected amount, and we'll label it as nominal, meaning we didn't test it, but according to our grade library, you should expect it. It's a heads up to the user that there's light element there. And then if you want to actually test for the light element, instead of testing a short amount of time, you can run longer, about 20 seconds in this case. And I've got actually a reading here that shows the aluminum at 1.3%, and it's pretty close to what the aluminum is in the sample. It's a nice result. So we can, if you want to measure it, you can run longer. If you just want a heads up, the system will let you know that you should expect it. Another way that we can optimize what we're doing is with a camera collimator. We're looking at the display on the instrument, but we've selected to view not data or the ready screen, but actually the camera that's looking out through the window on the instrument. We have an option here to make the beam spot smaller. This is the 3 millimeter beam spot, and over here is a 10 millimeter. 3 millimeters is about 1/8 of an inch. 10 millimeters is toward 1/2 an inch. And basically, in this case, the entire beam spot should be striking only the piece of brass that I have sandwiched between 2 layers of stainless steel for this test. In this case, my beam spot is hitting stainless steel on either side of the copper grade. So if I go ahead and look at the results from these 2 tests, in the first one, we've got, we ID the brass as 360 free cutting brass, also known as yellow brass. Comes up fine. We don't hit the stainless steels, just the brass. And then the view on the right, the 10 millimeter shot where we're hitting them both, we come up with no grade ID because we mixed them both together, and you can see we've got 23% iron and 10% chrome, nickel. These are things that wouldn't be in the brass. We're getting them from the stainless steels, and the chemistry doesn't match anything because it's a mixture of the 2. So the camera collimator can benefit you in that when you're trying to get a grade match, I'm going to back up a little. When you're trying to get a grade match, if you grind the material and then you shoot and you miss the spot that you've cleaned, you won't get a grade match. You might see high zinc or copper or titanium from the paint. And typically what people do is they know that they missed because they got paint ingredients when they shot. They'll grind again and try again. If you have a camera, you can see what you're hitting. And if you make your beam spot smaller, it's easier to hit the spot that you've prepared and not the painted area around it. So this can improve your productivity to be able to see and hit a spot that's not easy to view. Here we have, again, a view of the collimator size beam spot on a weld spot. Another thing that can save people that need to do PMI inspections a lot of time is the ability to test a hot sample. Instead of having to wait for the plant to be shut down, you can actually go out and test up to 900 degrees Fahrenheit, 480 Celsius. Oh, we got a little typo there. It should be C. Anyway, the system is built to basically radiate the heat away, to wick it away, to handle hot testing. The key is, of course, to not stay on the hot pipe for a really long time. So being able to do a quick test like we can with silicon drift detectors and get good precision and good grade ID in a very short time enables us to better do hot testing. But we have a customer in particular that did 93,000 hot tests over 600 degrees Fahrenheit on one project. The system, as long as you're running no more than about 60 tests an hour, you really don't have any difficulty handling hot samples. We recommend 7 tests not be longer than 7 seconds, that you stay off of things that are higher than 900 degrees Fahrenheit. I think you could go a little higher if you wanted to. You just wouldn't be able to test as frequently. You can't do light element testing. We can't do 20, 30-second tests, not only because of the duration of the test, but also with light element testing, we use a clear proline window. Proline will melt, so you need to use the cap-down window, which is not as friendly to the lighter element X-rays, but handles the heat just fine, as long as you keep your tests under 60 tests per hour. And then we have a tilting technique that we use when you get on hotter samples. Basically, this is the window end. You just raise the bottom, this part right here, up a little bit off of the sample so that you minimize the heat transfer. It doesn't affect your measurement precision significantly or the time. It's a good way to do it. And anyway, you can see here we show flush testing, which is the normal way you would do things, especially when they're not hot. Tilting, which you can do on a hot sample to minimize the heat transfer. And we have another option, which is a ceramic heat mask that goes over the front of the analyzer to shield it from the heat. We wanted to test and see which worked better, the heat mask or the tilting. And we did a test and collected data, and basically our detector is cooled down to minus 40 degrees C, and we looked at how much current or how much voltage had to go into the Peltier cooler versus time to see how well the instrument was doing for staying cool while we were on a 900 degree Fahrenheit sample. So we did 5-second tests, 1 a minute for 90 minutes. And what happened here is that the tilting technique, the amount of voltage that was required to keep the detector cool never really got as high as the mask unit did even in 15 minutes. When we got to about 90 minutes, the mask unit actually got to the point where it couldn't keep the detector cool enough, and it had to shut down, whereas the tilt system really was sort of a steady state at that point. I think you could test all day without any issues on a 900-degree pipe if you're tilting. So being able to test in-service hot stuff, you don't have to wait for a shutdown. It doesn't limit your ability to get your project done. Doing the material testing as part of PMI testing, I think, is the easy part. It's point and shoot. We can handle sample prep and hitting the spot and handling high temperatures and getting the answer reliably and quickly. The harder part is that there are miles and miles of piping, thousands of components. You've got to make a plan. You've got to test it. You've got to track it. You've got to decide that things are what they're supposed to be, correct it if it needs it, and then finish the job, complete the job. And to do that, you need some kind of a system to manage all of those variables. And I'm going to pass things over now to John Bailey, and he's going to talk to you about his tablet-based PC system. Thank you.
Okay, well, thank you, Ken. Well, I'd like to just take a little time here just to give you some of the the benefits as well as the functionality of my tablet-based system. Well, it's kind of a little bit further than the tablet. The tablet is the portion that actually interfaces with the instrument, but there's other aspects of it involved, and we'll discuss that as well. The PMI project, less than 10% of the time is spent actually pulling the analyzer trigger. There's lots of other aspects of the project that start from the initial identifying what's the scope or identifying all locations that need to be tested to the verification that you've actually collected the data for those locations, and then also the managing the remediation, any of the issues that were identified during that project. So there's many aspects, and those other aspects can be quite time-consuming and take a lot of resources to do it properly. So basically, the approach that this system, the solid PMI system, takes is to, first of all, simplify access to the information that's needed to perform these projects. Second goal is to simplify the validation process. That's really where it gets challenging on these paper, the systems that are available for use. Is, most of them are paper-based. You're writing your results on paper, and just knowing when you've actually collected data for every single location can be quite overwhelming. And then, of course, you need to develop some reports. You need to be able to pass on any findings to people for remediation, the maintenance departments or whoever is going to be responsible for those. Or it might be an inspection department to monitor these, locations that might not be totally up to required standards. And then, of course, the main source of a lot of this information is the mechanical integrity software packages, and there's several of those that are available, and anything from Meridium to Credo to PCMS, UltraPipe, and many others that people use in their facilities. To be able to interface with them, that's definitely beneficial. So basically, this diagram here illustrates how the system can access that information. First thing to point out is the actual interface that it makes to the client databases, whether it's for maybe a process safety management type database that might have some details in there, or it could be a mechanical integrity system, such as, like what we said, PCMS, UltraPipe, Meridium, or, many others. And then also, a lot of times, there's work orders that need to be issued to resolve some of these items or that need to be resolved. So that's a beneficial link. Then there's the documentation that you need to be able to access to actually perform these projects. Like, for instance, your CAD drawings that actually contain the schematic, your map of what's going to be tested. There could be other documents and photos that would provide some beneficial information. And then we get to the other side of this flow diagram, which is the access. Once all those links are established and then they're translated using those adapters in those previous slides, then it can be presented in a consistent format, no matter what type of database you have for mechanical integrity. Once you bring in that data that you need for your project, then it's made available in the web portal, which it has a few different functions. Basically, it has some basic KPI metrics types reports. It provides access to your documentation in a little bit easier format, kind of like your Windows Explorer, and some other tools. But the area of interest for this is the interface with the tablet application. Basically, the system is able to package up all those details that it's able to access through those converters or translators to the native formats used by the company that's doing the PMI project, and delivers them to the tablet so that the tablet can then manage that data and then add in the PMI data that's going to be collected from the instrument, which is illustrated here. When the solid PMI, that's the tablet application for actually performing this PMI application that we're going to see a few screenshots from here in a minute. It can interface through the Bluetooth interface, like what Ken mentioned earlier, to the actual handheld XRF alloy analyzer. this screen here, once that data is made available and there's some translation that's going on or imports of the native data, you can run reports, in different ways. You can filter for what circuits or equipment is of certain types of materials. You can also filter by service or, different other parameters that would be beneficial to identify what equipment would benefit from a PMI project. This next slide is from the scheduling system that is part of the website. It basically pulls in, activities that need to be performed, and in particular, these alloy circuits that are identified. Once those are identified, then they can be scheduled, and then by utilizing this export to tablet button here, you can then export all that data to your tablet, to the tablet application, so that you can perform the actual PMI project. This here illustrates how overwhelming the quantity of data can be for these PMI projects. Basically, what you see here is how people are forced to conduct these PMI projects if they don't have a system, a custom system like what we're discussing. Basically, the illustrations, the drawings that are used have been used, they're developed for the main purpose of tracking and managing the locations for the TML or your thickness monitoring that's part of your mechanical integrity program in PCMS or Meridian, the different type programs. And when you compare the number of PMI locations to the number of these thickness monitoring locations, you're looking at least 20 times the number of locations, because where in a TML type inspection program, you do a lot of representative sampling. You're not measuring every single component of a piping system. You're selecting certain locations and, based on the whole system being made of a specific alloy, certain design standards. So you're able to do that representative sampling. But with the PMI project, you have to evaluate 100%, because the PMI project is the basis of knowing that system has been, it qualifies that representative sampling. It allows you to have some confidence in doing that in some of your other inspection programs. If your system is not built as designed, there's certain areas that do not meet requirements. You cannot use the representative sampling that those other type inspection systems are based. So the system basically, this is a report that was generated from the actual tablet. Basically, once you go to the field and you have your instrument linked and you've downloaded your packages to the tablet that show your drawings and your systems and your circuits and what are your alloy requirements for each item, as soon as you are through collecting that data, you're immediately able to generate reports such as this. And this report here, the value of running these reports in the field is that you're able to see and identify all your locations and verify that they're complete. This drawing here, there's different colors that are assigned to the different types of components, and that's really advantageous when you're looking at a piping system or an ISO drawing. I've seen drawings that have over 600 analysis on a single drawing, very congested. And to be able to have a system where you can easily see, hey, have I identified all different types of components, which this filter allows you to do. This here, it's filtered to only display the elbow locations that are, needing to be tested. So you turn this filter on and you can easily see which locations, have you identified all these elbows. And if you look on this drawing, there's actually an elbow there that was not identified. There needs to be a test location added there. The other types of reports that can be generated while you're in the field or, back in the office, either way, is a report that shows any potential nonconformances, a simple filter that allows you to highlight any of the locations that do not match the specified material that was downloaded from your mechanical integrity system or, whichever way that scope, that information was obtained, you're able to compare that against the measured values that are associated with each one of these locations. So any location that does not meet spec, you apply a simple filter. Every location is highlighted. You can do a verification shot if you wanted to, or similar reports to this can be provided to maintenance for, as a work list to go out and remediate any of these issues that are identified. This slide here basically, that area that says readings per TML, basically what this is, it's one of the ways that the system is intended to maximize the use of your space that's on these drawings. Basically what it allows you to do is if you have a location that you want to identify that has multiple shots, some types of components that you test might require, 2, 3, maybe even 8 or 10 different analyses. And what you're able to do is to not only say there's so many readings per location, but you can name those particular components. Let's say, for instance, a vent bleeder. You have a bleeder coming off of a pipe, and starting at that base weld between the weldolet and the base pipe, to the weldolet, the weld between that weldolet and the nipple, so on and so forth. There could be 8 different locations for analysis. And to be able to group all those tests together in a single location on your drawing greatly simplifies the drawings and your reporting and everything else associated with it. Okay, another advantage is when you are performing a PMI study, like we discussed earlier, basically most of the drawings that are utilized for these projects have been used for your corrosion monitoring, your TML monitoring programs, and linked with your mechanical integrity database. You will never look at these drawings or any of this piping to the level of detail, as when you're performing a PMI study. There's going to be some areas that you might need to collect UT thickness data. If you identify a discrepancy, it would be nice to be able to immediately shoot a thickness reading. And, of course, my system, since it communicates with Bluetooth, I've got systems and ways of communicating with the UT instrument if you want, or you can, take the reading if you don't have a Bluetooth-enabled device and type in your reading that you get while you're there. And so you can collect all that data at one time. Other things that are beneficial is maybe capturing a photograph that's associated with that circuit that's being tested. It might be that you need to do, some updates to those ISO drawings. Or, you're looking at every single component in there, you're going to see some issues, some visual observations that you might want to document. And having that capability as well in this tablet application is very beneficial. And then also, while you're performing this inspection, maybe you want to take some surface temperature readings and utilize maybe a Bluetooth temperature probe and upload that data and associate it with a test, a location where you have kind of a sanity check on what the actual operating temperatures are of these lines that are being studied as part of the PMI project. Basically, once you've collected all your data, like I mentioned, you're able to generate a lot of reports while you're in the field that mainly help you come back to the office knowing that you've completed the full scope of the project. When you're back in the office and you're able to upload that data back to the website, then you're able to see the actual detailed results of each item. There is a way also on the tablet in the field, but a lot of people, this is how you'll be able to access that data in, long term to be able to see the raw data, as well as with the translators that are part of the system, you will be able to upload that into the format either through an export utility or different ways to get it back into PCMS or whichever mechanical integrity program if you would like to do that. It can be done at a detail level where you actually upload all these different circuits, or it might be all you want to have is a summary report showing, hey, all test locations for this particular drawing met requirements, or they, any issues were remediated, and you might just want to show that summary report showing that, there's different options, different reports that are available. So at this time, I'll pass it back over to Ken and let him wrap things up. And thanks everyone for your time. And if you have any questions, just let me know.
All right. Well, thank you, John. Thank you, everybody. We're just gonna wrap things up here. Plant PMI is an enormous task. The XRF, basically, with the advances in the detectors, can perform much faster testing, give you better analytical confidence, better throughput. The camera collimator and the ability to see that you're hitting the clean spot on the sample, you can get better productivity. The design that allows you to handle temperatures up to 900 degrees Fahrenheit is something that makes it much simpler to get your work done. You don't have to fit it into a tight little spot when things are shut down. So these are all things that we hope will be of interest and have been informative for you. I know that John's inspection management software is a really powerful and unique tool. John's, we're just one kind of a front-end sensing device that is compatible with John's product. John's independent from OLYMPUS, but we're pleased to be able to integrate with his system, allow you to get massive gains in productivity. So we hope, again, this has been useful to you as we've taken you through the flow of a PMI tool, an XRF, and a management system based on a tablet PC. We're ready for questions and answers, and we do have some questions, and I'm going to just look at them and read them and answer them quickly here. I got a question: how accurate is the reading compared to a sample set sent to a lab? The primary difference is that we don't measure all of the elements that the lab would measure. We don't measure oxygen or nitrogen or carbon, so those samples are missing. We normalize what we measure to 100%. This allows us to measure odd shapes in the field, small pieces, things like that. The laboratory, a certified metallurgical laboratory, will have a tighter precision than the field instrument will, but our instrument will give very similar measurements, and really, if there is a variation from the lab, for it to be different than what you were seeing in my slides, would really have to do with the sample preparation or whether it was clean or not. If the sample is well prepared, the results that I got are the results on certified samples. Comparing it to the laboratory, you can see that there is analytical agreement between the two methods for elements that are measured, is what I would say. We got a question about, says we test for lead in surface coatings for CPSC, consumer product safety. Can you speak to that? And I can. Very briefly, we have a product with an algorithm that is optimized for consumer product safety. You can get some information on our website about it. You can talk to anybody that you'd like to about how this technology gets used for that application. We do have a group that does that, and it does work. You could get it on the alloy analyzer. It would be a separate mode, and you would switch from alloy to coating type testing. I think I'm going to pass on that question. Which element is T? That's a very good question. The element is phosphorus. It's a typo in my little log of the information, and it is phosphorus. So I'm glad that question came up, and I can clarify that point if anyone else was wondering. I think that is as much as I'm going to, let me see, I have to confirm the composition of a shaft made of 17.4 pH. Am I able to determine that my shaft is really made of 17.4 pH? You would need a clean surface sample. Probably it would be fine without grinding. 17.4 is a grade in our library. It's close to 15.5. That's the nearest thing that would cause you trouble in identifying it, but it shouldn't be a problem to test that and verify it. Any special license required for radiation? The regulations are different everywhere in the world. Typically, there is no license required because there isn't any radioactive material. Licensing is typically defined as, a license for radioactive material. We're using what's called electronic product. We produce our X-rays electronically, but there is typically registration is required, and that is you do have to notify your regulatory body typically, and they usually want you to send them a check for $50 to $500 depending where it is. Can smaller parts, less than 3 millimeters, for example, be analyzed? Is a calibrated known surface holder a possible way? This is a good question. Basically, we can do tiny parts that you could barely see. The issue is that you need to test only that part. Typically, it's done in a test stand where the sample is set with tweezers on the window and analyzed. If you were to put a known material there to hold it, the known material that I would recommend would be some kind of foam that would have no signal at all. You wouldn't be able to subtract out a piece of stainless steel from a carbon moly steel or anything like that. So you would want to isolate the material and test it, but we can test very tiny pieces. Can sample surface have different contour, or must it be flat? In the same way we can test very small pieces, we can test any shape. If it's big enough to see it easily, we can test the shape. The critical thing is homogeneity, that the sample needs to be homogeneous and it shouldn't have any kind of surface contamination that will interfere with the measurement. Printout of analysis report or export into Excel, we can do both. Do we offer training certification for Chevron? We don't do training. We've talked about it, but we don't. I think that's as much time really as we have for questions. We will endeavor to answer all of these online or by email. Want to thank everybody for listening and for asking questions if they did. And so, again, thank you very much.
Oh, thank you, Ken, and thank you, John. On behalf of Olympus, thanks to both of you guys for your participation in today's event. It was very informative. Thanks very much to all the attendees for joining us. We hope you found the material useful. This webinar, along with Q&A from this morning's session, will be available on our website at www.olympus-ims.com by early next week. Please feel free to check the website, and there's an awful lot of information there. That's going to do it for today. And again, thanks to everyone for participating, and we will see you again next time.